19th International Physics Olympiad, 1988 year. IPH. Problem 3. Recombination of positive and negative ions in ionized gas. Theory. Introduction. A gas consists of positive ions of some element, at high temperature, and electrons. The positive ion belongs to an atom of unknown mass number Z. It is known that this ion has only one electron in the shell, orbit. Let this ion be represented by the symbol Az-1+. Constants are given that may be useful later. Question 1. Assume that the ion which has just one electron left the shell, Az-1+, is in the ground state. In the lowest energy state, the square of the average distance of the electron from the nucleus, or a square with components along x, y and z axis being delta x square, delta y square, delta z square respectively, and our 0 square equal delta x square, plus delta y square plus delta z square, and also the square of the average momentum by p0 square equal delta px square, plus delta py square, plus delta pz square, whereas delta px greater or equal Planck constant over to delta x, delta py greater or equal Planck constant over to delta y, delta pz greater or equal Planck constant over to delta z. Write inequality involving p0 square multiplied by r 0 square in a complete form. Question 2. The ion represented by AAZ-1+ may capture an additional electron, and consequently emits a photon. Write down an equation which is to be used for calculation the frequency of an emitted photon.
Question 3. Calculate the energy of the ion Az-1+ using the value of the lowest energy. The calculation should be approximated based on the following principles. 3a. The potential energy of the ion should be expressed in terms of the average value of 1 over r. That is 1 over r0, where r0 is given in the problem. 3b. In calculating the kinetic energy of the ion, use the average value of the square of the momentum given in 3.1 after being simplified by p0 square r0 square approximately equal Planck constant square. Question 4. Calculate the energy of the ion Az-2+ taken to be in the ground state, using the same principle as the calculation of the energy of Az-1+. Given the average distance of each of the two electrons in the outermost shell, same as R0 given in 3.3, denoted by R1 and R2, assume the average distance between the two electrons is given by R1 plus R2 and the average value of the square of the momentum of each electron obeys the principle of uncertainty. That is P1 square R1 square approximately equal Planck constant square and P2 square R2 square approximately equal Planck constant square. Hint: make use of the information that in the ground state R1 equal R2. Question 5. Consider in particular the ion Az-2+ is at rest in the ground state when capturing an additional electron and the captured electron is also at rest prior to the capturing. Determine the numerical value of Z, if the frequency of the emitted photon accompanying electron capturing is 2.057 multiplied by 10^17 radians per second. Identify the element which gives rise to the ion. Solution to question 1. According to the condition for coordinates R0 and momentum P0, we have the following relations. Since the uncertainty principle holds for momenta the following inequalities, we have the following inequality for expressing P0. Due to symmetry, the following relations hold for coordinates. Substituting them into the previous formula yields the following inequality. P0 squared R0 squared is greater than or equal to 9/4 of Planck's constant squared. This was the solution to question 1. Solution to question 2. Let VE is the velocity of the outer electron before capture. VI is the velocity of Az-1+ before capture. Vf is the velocity of Az-1+ after capture. hν is the energy of the emitted photon. Then the law of conservation of energy gives equation 1. Here EAZ-1 plus and EAZ-2 plus denote the energy of the electron in the outermost shell of the ions AZ-1 plus and AZ-2 plus respectively. The law of conservation of momentum gives equation 2. Here vector 1 is the unit vector indicating the direction of motion of the emitted photon. Thus, the equation that will be used to calculate the frequency of the emitted photon is given by formula 2. This was the solution to question 2. Solution to question 3. Definition of energy AZ-1 plus. Potential and kinetic energy are defined by the following expressions. If the motion of electrons is limited to the xy plane, the uncertainty principles of 3.1 can be written as follows. Hence P0 squared is equal to the following expression, which gives P0 squared or 0 squared is equal to h squared. Formula 3. That is, the total energy is equal to the following expression using formula 3. The minimum energy exists when the first derivative with respect to R0 is equal to 0. Hence we have the following expression. Hence 1 over R0 is equal to the expression 4. This gives the following expression for energy. Formula 5. This was the solution to question 3. Solution to question 4. In the case of AZ-1 plus ion captures a second electron, potential and kinetic energy of both electrons are next one. Potential energy due to interaction between the two electrons is this one. So total energy is in expression 6. Total energy is lowest when first derivative is 0. It means that after 6 we have expression 7. And 1 over R0 equal expression 8. Finally total energy of the ion AZ-2 plus is in expression 9. That was solution to question 4. Solution to question 5. The ion AZ-1 is at rest when it captures the second electron, also at rest before capturing. From the information provided in the problem, the frequency of the photon emitted is given by this expression. The energy equation can be simplified to expression 10. Using previous results we will get expression 11. Putting in known numbers follows equation 12, which can be simplified to 13. With the physical sensuous Z is 4.1. Expression 14. This implies Z equals 4, and that means beryllium. That was solution to question 5. So we discussed all 5 questions to problem 3.